guess we'll start. Welcome everyone. So this is Theorem Proving in Lean, and it seems that this is going to be a big class, so I'm happy to see you all here. I guess I'll start by sort of introducing the setting where we're going to be working here. So there's a, actually I'll just skip here a little bit to mention that there is a there's a course website, so that's this here. If you haven't already found it, it was linked in the initial announcement, and that's this here. But there's also a course repository now. That's this one here, and this is where I'm going to be posting the lectures and other pieces of code. So this is Lean repository, and I'll introduce you to it in a bit. Okay, so also I guess I should introduce the people involved in the class. So there's me, the course responsible. For PhDs and master's students, we actually have two examiners. The here is for the PhDs, and for the master's students and above is the person responsible for that. And so basically, if you have technical details to do with your enrollment in the class or things like that, then see one of these two people for that. In case you weren't already aware, this is a class on learning the Lean Interactive Theorem Prover. The reason why you might be interested in this tool in particular is because it has a variety of applications for doing verification, for why you would want to use interactive theorem provers in the first place. I guess I should start. One of the reasons is that you might want to prove the correctness of a mathematical theorem, right? But you want to do so in a way where the computer's checking that it makes sense. It's also a way of producing sort of formal artifacts. So you have a library of results, and now you can show it to other people, and they can learn about the mathematics, and they can interact with it in their own way. So it's a useful way of doing reference or search type activities. It's also a way of doing collaborative development of mathematical theorems. So if you have a bunch of people involved in checking a theorem, you might be working on one part of it, but then you have some well-defined subtasks that you can give to other people, and having computers assist with that is useful. Teaching and learning. So this is like if you're trying to teach someone how formal logic works, one useful way of doing that is if you have a system that tells you, yes, this is right, no, this is wrong. This is very useful for getting sort of instant feedback on how the rules of the game work. And then you can use this for exploring or doing mathematics, just sort of knowing what's out there by browsing these libraries and developing your own stuff. And as a formal artifact, it's also useful as an input to machine learning and automation activities. Question?
Could you make the font big?
Oh,
larger?
yes.
It's difficult to
I'm
read.
quite
Okay.
sorry.
Thank you.
Okay. Yes. Let me give you some links to interesting things. So I already mentioned this is the course webpage, and this is the class material webpage. There are two main resources, I would say, for the basically this is the Lean community webpage. This is where an organization called Lean Prover Community puts all of its things regarding to Lean resources. And so in particular, MathLib is a Lean library, and it is maintained by this organization, and you can see sort of how work has been proceeding. And so like here we can read that we're almost 1,700, yeah, what is it, 1,700,000 lines of code in MathLib now. So this is work on all kinds of variety of mathematics, and there was a switch from these two lines are from the Lean 3 version to the Lean 4 version. We're going to be using Lean 4 in this class. Yeah, so it's quite an active place, and also if you're interested in using pieces of MATLAB, this is a good way to access various. So this is like the API documentation for MATLAB, and so this has tons and tons and tons of theorems and so on. There's a search here, and so this is a way of finding things in MATLAB, but we're probably not going to be doing that for a while. And then this is the Lean webpage, leanlang.org. So if you just type in Lean and search for it, you're probably going to find this. And in particular, what I would like to call attention for you all is the official instructions here for how to set up Lean. So you're going to want to do this at some point, either like right now or maybe after class, because I'm going to be going through a Lean worksheet for most of this lecture, and it would be helpful if you can follow along in Lean itself. So just go here, and this explains how you can set up Lean. The basics are you install VS Code, you get the Lean 4 extension, and then there is a setup guide that you can just click the go buttons and then it will install Lean. As for things that interesting news stuff regarding Lean, just so that you can be like, wow, it's cool. Here's Terrence Howe talking about how Lean is awesome. And here's a page about Alpha Proof, which is a recent machine learning system by DeepMind that was able to solve a bunch of IMO problems, and they did so using generation of proofs using Lean as a sort of sounding board, I guess, to check whether the things are correct. But okay, and then the other thing that I want to mention is that there's a private channel on the Lean Zulip. So leanproof.zulipchat.com is the Lean Zulip instance, and there is a ton of chatter here about all things Lean related, and I'm going to be using this private stream to be able to communicate with you all. So your assignment for today is to sign up for this and then DM me, so you can find Mario Kart and then send the DM saying I'd like to be added to this private stream, and then I'll add you, and then all future communications regarding course events and or things that I would like you to know will be sent through this. Okay, and you can see, so all of these are linked here on all the things I just showed, and you can get this lecture 1.lean on this the course repository. Okay, so all right, so the just general course administration stuff. So the goal here is we're going to learn to formalize mathematics and Lean specifically. This is a project course, so that is to say all of your grade is going to be in the final project. There are no exams. There might be some assignments, but they're not going to be for credit. And I'm mostly just going to be giving these lectures in an editor like this. The plan is that for the first 3 or so weeks, I'm going to be giving lectures like this, and just sort of showing you how various aspects of Lean work. And then the second half of the course, we're basically going to break up into doing projects either in individual or in pairs. So the idea is you're gonna come up with some project idea, maybe related to your own research elsewhere, and we're going to build something lean related, and that will be the project. So in the second half, it's mostly going to be me meeting with you all to talk about your projects and your plans and that sort of thing. Okay, so just so you keep this in mind, this is going to require some independence and time management skills on your part to be able to produce something interesting by the end of the class. Okay, so I already said this, information is going to be on the Zulip chat, and your first assignment for now is to sign up for Zulip and DM me. Okay, these lectures are being recorded, I'm recording right now, and I will post them on the Zulip as they become available, so that way you can, if you were not able to attend a class or something like that, I will be putting them on the Zulip stream. Yeah, and you can use GitHub to pull these lectures and any assignments if there are. So there are two main textbooks we're going to be using. One of them is Theorem Proving in Lane 4, and the other one is Mathematics in Lane. So today I think I'm mostly going to be covering chapter 2 of Theorem Proving in Lane 4. Okay, and good. Describe this. Okay, so we need to install Lean, and to do so, you follow the quick start that I showed you earlier, and you'll also need Git in order to run these lines of code. So this is basically so this is saying clone a repository, go into the repository, and then run these two lines, lake exe cache get, and then lake build. And then that will compile this project, and if you open up, so I'm currently inside that repository, so if you go into TPIL 25, lecture 1.lean, then you should see all of this stuff that I've got down here. So then we'll be on the same page. Okay. So, questions?
Can I ask about the insert? So I installed using VSC Code, but I don't know where the binaries are on my drive, so they are not recognized from the shell, so lake is not known.
Okay, so that might be, it should be installed in a global location, so you might try either restarting VS Code or restarting your computer, and it should actually update. Like it might just not have updated in your current session, but I believe it should install globally Elon, which is the thing that manages Lean, such that when you are inside this, then Lean will work. So like if I go here, then I should be able to run lake build like this, and if it's working, then you get something that looks like this. Yeah, that's working. Okay, and if that's not the issue, then you can come talk to me after class. Okay, any other questions? All right, so let's talk about Lean itself. So Lean, you have basically a single language for defining data types, defining objects, stating claims, and writing proofs. And so at its most basic level, Lean is a type checker. So you write down expressions, and those expressions have types, and when you ask Lean to check that this thing has a type, it does so, and then it tells you, and then you know that it has a type. The two fundamental operations that you get are to check that an expression is well formed and either infer the type or check that it has a type that you specify, or to evaluate an expression if you're given such an expression. So just a quick overview here. So we can define constants. I say m. So I define m is a natural number to be 1. And then I define n to be 0, b1 to be true, and b2 to be false. And now if I say check M, then it tells me M:nat. Now, just some bits of info here regarding what's going on. So when I write down, I can, if I write down check M, you can see that it says, it puts a blue squiggle here saying that it's trying to output something. If I hover over it, I can see what it's outputting. It also shows over on the right side in this sort of phantom area, it also shows the value. This is actually a VS Code extension called Error Lens. So if you just install VS Code according to the instructions, you won't see this particular part, but you will see it here. But if you do like this, then you can just install the Error Lens extension and then that will happen. The other thing is that there is a sidebar. So if I believe you can get to this sidebar by selecting Toggle Info View from this upside down A. So this is the lean menu here, and so you say Toggle Info View, and then it brings this up. And so when you're paging around here, when I am on a line that has a check, it shows the output of the check over here. So that's how that's how this works. All right, so good. And then I guess you can also see here this yellow bit. That's lean compiling the file. So normally when you're writing here, anything that is in this part of the window is being checked. If I make modifications, then it updates and so on. So that should be as expected. But okay, so here we're checking the types of some expressions. So we say M is nat. And so I asked, what is the type of M? Or like, is it well typed? And if so, what's its type? And then it says M:nat. This is, boldface nat. And n+0 is also a nat. So basically just doing operations on natural numbers and booleans. The double and here is boolean and. A double or is boolean or, and this is true. Okay.
Why does nat come out into shapes?
Oh yeah. So I can. Okay. So these two are the same thing. One of them, you can either write it with. So if you should get this if you have lean installed. There is a mechanism for you to be able to type special characters. So here, if I type \N, then it gives me a this boldface N symbol, and this is the way that you can write nat. If this, I believe, if I just comment this out, So this is actually a mathlib addition that you can write it with this notation. If you don't have mathlib, then it's going to complain that doesn't exist. But just so you're aware.
So it's expressed somewhere in lean code.
Yeah, so in the mathlib library, nat is defined in lean, but the notation of this boldface N for nat is in mathlib. So that's what that is. Okay. Also, I just wanted to mention that example is another variation on check, you could say. So check it calculates the type of this thing, and then it tells you using the blue squiggle mechanism. If you use example, it's just type checking. So if I do one plus high, then it complains that this is not well typed, more or less. If I said that this was a string, then it also complains that that's not the case. But if I say it's not, then it works. So this is, just checking that this expression has a type. But this one doesn't report anything. It just checks. Okay. Right. And evaluation is you give it an expression and then you use it like a calculator, right? Like this is what you would get if you were playing around with Python or something. At the REPL, you can just write this. And so like a lot of people will, if they want to use Lean as a REPL, then they'll just write this in their editor, right? Rather than having some console mode or something like that. So that's just how you can do this. All right, and you can evaluate expressions that have been previously defined, like m here. So m was defined to be 1, and 1 plus 2 is 3. So good. And then we're not really going to be using this much, but I just wanted to mention that reduce also exists, and to first approximation it does the same thing as eval. There is some differences to do with the fact that eval is turning your stuff into bytecode and evaluating that, and reduce is using the core rules of the type theory, but basically reduce is a slower version of eval. The first approximation. Okay, so sort of starting with simple type theory here, we can construct types that are function types. So this is the type of functions from natural numbers to natural numbers. And you can see that here. You can write it. It's probably not obvious here, but this is an ASCII hyphen and then a greater. But I'm using a programmer font which makes them look sort of similar. Whereas this is a Unicode arrow, I can get this with \r, so or \2. And similarly, so this is function types. This is product types. So you can write \times to get this little x here, or you can just write prod. But why would you want to do that? But this is sort of how that's actually constructed. These two are the same.
Yeah, so sorry, I'm maybe wasn't paying attention. So all the blue stuff and the red stuff on your screen is from this editor extension?
So the blue squiggles are.
Oh no, I like the blues, like the.
Yes. So the
Yeah.
stuff on the right here, these are all from the arrow lens extension.
Okay.
So.
And the red error messages too.
Yeah. If I just write something wrong, then you get also red error message here, and so this is useful. Okay. Right, and the arrow is right associative. So this double arrow expression means the same thing as just occurring that way. And then if you associate it the other way, this is a function from functions to the natural numbers to a natural number. So this might be something like evaluate at 0 or something. Here's some examples of terms of these various functions. So like nat.suck is the successor function on the natural numbers, and so that's something that has type nat, arrow nat. 0, 1 is a pair of natural numbers, so it has type nat times nat. And then nat.add is a binary function. And in general, in Lean, when you have multi-array functions, they're going to be written in this curried style here. So that is to say that you have a function that takes a function that takes a function that eventually returns your result. And since I'm assuming that you all have some familiarity with functional programming languages, this should not come as a surprise. But this is sort of a standard approach to handling this. Okay, so nat.suck2 is like the number 3, right? But as an expression, it's just the successor of 2, and that's a nat. Nat.add3 is a partially applied nat.add, so you get just a function which is waiting for a value and then returns 3 more than that value. But then if we apply it to another argument, then we get a nat. This .1 and .2 is a way of getting the first and second projection of a pair. Okay. So
are there tuples of other sizes as well? Or
yes and no. So if I write this, that works. But what it actually means is this. So there's actually only a binary product, and then it's just right associated. Right.
So just to clarify, you would then, to get the 9, you would have to do .1.1,
Right. So here, if I
Or
wanted,
go to.
yeah, exactly. So if I wanted the 3 values, I would do that. Yes.
And dot 3 does give an error.
And n.3 gives an error. Okay. Oh, and this is just showing that you can also evaluate these expressions. So this was just checking that they are well typed, but then you can evaluate them if they are well typed, and you can see that if you take the first projection of 5, 9, you get 5, and the second projection is 9. Here I just wanted to show some things about so this colon thing, this is called type description, and this is saying I assert that this subterm has the following type. And this can have effects. Here I wrote 2 plus 2, and I get a natural number 2 plus 2. But Lean has a way of interpreting numbers into arbitrary types, and it's sort of taking that by default, but you can have other types as well that have a 2. So here I'm saying 2 plus 2, but the first 2 is a real number. And so now you notice it says, oh, 2 plus 2 is a real number. And that's because it determined that, well, you wanted real addition here. So this is the real addition function between 2 natural numbers of type real. We can sort of do the same thing on the outside where we say, I expect the result of 2 plus 2 to be a real number, and then it figures that everything inside is the real number as well. Okay. But we can also evaluate these expressions and, here we're doing evaluation. Maybe I should give another example here. So if I do evaluation 17 divided by 5 plus 5, we get 8, which is not what you might think this expression should be, but that's because this is interpreting everything as a nat, and this as nat division, which is truncated. So, okay. But then if we put in q, so this is using rational number division, then it gives us the sort of exact rational value, 42/5.
So on the line above, if you were to ascribe that second 5 to be a q,
Then it would also be 42/5.
would it? Okay.
So this is using type inference to basically, since this is a q and we're adding it to something, that thing also has to be a q, and since we're dividing 2 q's, they also have to be q. So everything has to be q, basically.
So if you have something that is definitely an n and you add it to something that is definitely a q, that'll be a type error.
Then a different mechanism triggers. So here, we can also coerce natural numbers to rational numbers. So here we should get 8, but the 8 will be a rational 8. So we calculated 17/5 as a natural number, but then coerced it to a rational number in order to perform this addition.
So what is the type of plus?
In this, actually, let me see whether, oh, you know what I should be using is check, and then it will be more obvious what's going on. So, the little up arrow here has indicated that there is a explicit cast that has been inserted from that to rational number, because that's the only way to resolve this. It sort of tries not to insert those up arrows unless it has no other choice. In this case, it had no other choice but to add it. But the plus, you'll notice the number of q's here. This is a plus on q, right? Whereas if I take this away, I can hover this and you can see all the n's. This is the natural number plus. I don't want to explain all the details of this add notation, but basically these are the 2 argument types and this is the return type. So nat addition. Okay. And then this is modulo. So modulo on natural numbers. Okay. Now, I mentioned at the beginning that everything is an expression and expressions have types. So types are also expressions. So nat is an expression whose type is big T type. So is bool, so is nat arrow bool, nat times bool. So basically all the types that we saw before on the right hand side of the colon, we can also put them down here as expressions and then observe that all of them are of type. So then the natural next question is what's the type of type? And the answer is that the type of type is type 1, and the type of type 1 is type 2, and then we see this sort of increasing chain of types of types, also known as universes. Here we have just showing that we can operate on types in the same way that we would operate on values before. So we have g is a function from a type to a type to a type. So if I apply g to, if I define a to be nat, so a is a type, and then if I apply g to a, then I get a function from type to type, and then if I apply that to nat, then I get a type. So nothing surprising here if we understand what's going on with just simple type theory. But now we can operate on types in order to produce more types.
Can you eval those things as well?
Good question. So what happens if you eval? What happens is that this thing is a type, and types have no computational content. So basically Lean says, I have nothing to do. I will optimize this entire expression away and do nothing. So there's nothing to do.
What if you reduce?
Excellent question. And that will demonstrate a difference between these two. So if I reduce this expression, actually that's an interesting result. One would think that it should say the product of nat and nat, but it has decided not to reduce it because it's in a computationally relevant position. So it actually does nothing in this case. But reduce can actually handle sort of all sorts of expressions. It doesn't actually care whether it's computationally relevant or not, but in some cases it might not actually reduce. Whereas eval is more like it's actually compiling it to sort of bytecode, and when it tries to compile a type to bytecode, it says, I have nothing to do. So that's the difference. Okay. And here's a table to maybe help a little bit with sort of picturing how these types and types work. So going sort of up in this is like this has type this, which has type this, but then prop has type, which has type 1, which has type 2, and so on. So that keeps going in that direction. So an example of a prop is true, an example of a proof of true is trivial, an example of a type is bool, and an example of a term of type bool is true. Or like there are also expressions that have type 1. So for instance, anything that's like an arrow, like type arrow type or nat arrow type, this has type 1. Let me just demonstrate that. So this thing has type 1, and then this expression here is an example of a function from nat to nat to type. So, okay. So we have all of these universe levels, but it would be annoying if we had to use concrete universe levels everywhere. In particular, list, for instance, is supposed to take a type. So this is the type of lists whose elements have type alpha. So list itself is a function from types to types, but it has sort of multiple variants. So like you have a function from type to type, but you also have a function from type 1 to type 1. So if you wanted to store a list of objects of larger and larger types, then you would need to use these other variants. And so list itself is actually defined with this dot braces u thing. It's saying that it takes in a universe parameter that tells it, is this type 0 or type 1 or type 2 that it's working on. And then it takes an input of type u and then returns an output of also type u. And so prod is also universe parametric. Here it has actually 2 universe variables because it takes 2 types from arbitrary universes and then produces another type in the larger of the 2 universes. So for instance, if I look at the value at 1 and 3, then this is a version of prod that takes something in type 1 and something in type 3 and produces something in type 3.
So is type 0 the same as type?
Type 0 is type, yes.
Can you also only instantiate the v and not the u?
I believe so, yes. So you can, this is really just the same as this. So I leave it undefined what variable I want, and then what lean actually ends up doing is it elaborates this expression, and then when there are unresolved universe variables, they get turned into these U1 things. So it doesn't know, so it's like, we'll just put in variable U1. Okay, so to create functions, we use fun. So you say fun and then the type of the argument, optionally with, you can either write it like this or like that, and then an arrow, and then the body. You can also use lambda if you prefer lambda. I'll usually be using fun. And then also, I believe you can use a maps to arrow if you're into that. Okay. And this is application. So here we have a lambda expression, and then we're going to apply it to 10. So this is x plus 5, and then we replace x with 10. So we get 15.
Can you pattern match in that notation?
Yes, you can.
Oh.
So let me demonstrate that. So let's say that I want to have, I don't know whether I can actually pattern match it right here. Yeah, I don't think that's syntactically legal, but I can say if I have a nat times nat to nat, then I can write x, y goes to x plus y. Oh, okay. Apparently 10 is actually a legal element of nat cross nat. It actually means 10 comma 10, which was slightly surprising to me, but because it's a ring. So MathLib has an instance of natural number literals for any ring, and the product of two rings is a ring. So anyway, all right. So here we have types as parameters. So you can use a function that has a bunch of arguments here. We're defining composition. And you can see here that like the types here are actually being used from earlier values of the function. So that's fine. That works the same as anything else. And also, I sort of hinted at this before, but propositions are also types in this setting. So true is a prop. So the type of true is prop. The type of prop is type. Type is type 1. Anyway. So true is a prop, false is a prop, 2 plus 2 equals 4 is a prop, 2 plus 2 equals 5 is also a prop. So all of these are propositions, that is, things that can be sort of true or false. So is Fermat's less than. So this is just the statement here. For all x, y, z, and n, if x, y, and z are not 0, when multiplied together, and n is greater than 2, then x to the n plus y to the n is not equal to z to the n. So this is a statement of Fermat's last theorem. And Lean will readily agree that it's a proposition. It will not so readily agree that it's a true proposition. So how do we show that these theorems are true? Well, we exhibit an element whose type is that proposition. So trivial has type true, for instance. 2 plus 2 equals 4 has a proof. That is to say, there is a term whose type is 2 plus 2 equals 4. And that term is REFL. Now this is showing a little bit, so our RFL is a proof of A equals A, and you might notice that 2 plus 2 and 4 are not literally the same thing. So this is actually showing some additional stuff that Lean is doing behind the scenes in order to observe that 2 plus 2 and 4 are actually representing the same value. And the way that we can tell the difference between true propositions and false propositions is that while the true propositions have proofs, the false ones, well, they don't have proofs, but I can still write sorry here. So sorry is how you say, I don't have a proof right now, but I don't know, go with the flow here, okay? So if I wanted to actually give it a proof, I could write something like by decide to try to prove 2 + 2 = 5, and it of course complains because it says, well, I tried and it's false. So probably not going to be proving this one anytime soon. Okay, and I'll explain a little bit more about by and tactic mode in the next lecture. Okay, so just keep in mind there are 2 different types, bool and prop. So capital T true has type prop, lowercase t true has type bool. This can be confusing, especially since Lean will also auto-coerce booleans into position. So like here I use this arrow, which is supposed to take 2 types, but little f false is not a type, but it can be coerced to a type by just writing equals true after it. So Lean will automatically insert this equals true in order to turn it into equality, which is a type. Okay. Are there any questions, by the way? Been going relatively fast.
How did you get your sorry highlighted?
I actually think it should come highlighted. There is, so sometimes, so like you'll notice here that the X, Y, Z, and N are red. So they will get highlighted like variables. This is part of a thing called semantic highlighting, and if you are not getting semantic highlighting, then these probably won't. They'll be like white with the same color as everything else. So if that's the case, then you can either try restarting the Lean server or getting a different, like it's also possible that some themes won't actually be showing these colors. So you might need a theme that has the colors, but the default one should have those colors. But if you have all of that, then you should see these sorries in some kind of reddish or, you know, badness kind of color. But the details depend on your theme. Okay, so good. And now I want to talk about definitions. So you can write a definition by saying def, and then the name, and then a list of binders, a colon, the type, the colon equals, and then the body. So the list of binders is optional. This is sort of equivalent to putting a function in the body and then also a function type in the argument. So you just write now here. So this double is equivalent to this double. And then also you can leave off the types of a definition. So you can just say, you know, this is some expression, and then just figure out the type and put it in here, right? So we can see that we have double and double and double are all the same. They have slightly different names for the variable, other than that, they all came out the same.
Are they equal to each other?
Excellent question. Yes. Okay. And then you can also have multiple arguments. So here, add takes in x and y's and that, and then it returns something where I let Lean figure out what type it's returning. If I mouse over this, I can see that it has decided that it returns that. And then I can evaluate it like anything else. Here we have a function. So the body of this thing can be any old expression, including more interesting stuff like if then else. So you can figure out what this does. Do twice is a higher order function. So here we're going to take a function as an argument and then perform that function to itself. So for instance, we can pass double the function to do twice in order to do double twice onto and get it. We can do more complicated things like having types as arguments here, taking a bunch of things, and this is just doing composition of any function types on any types. Okay, we can also do local declarations. So This is in expression position. We can write this down. We define y to be 2 plus 2, and then we can do y times y. So this is just doing 2 plus 2 times 2 plus 2, which is 16. Just as a formatting note here, we can, if we write it on a separate line like this, then we can actually leave off the semicolon. And so this is actually doing a sort of indentation sensitivity thing. Okay. Now let is sometimes considered to be equivalent to lambda and then applying it, but in this setting it's not quite the same. So the difference is that inside this context you can actually see here that A is defined to be nat, so it actually knows that A and nat are the same. Whereas in this context, A is not known to be anything in particular. It is a variable of type. So if I try to, so here I have x whose type is A, and then I try to apply nat.suck to it. Now nat.suck takes a nat, so the only way that this would type check is if x had type nat, and so it would have to unfold that A was equal to n. Now this works in this situation, but it doesn't work in this situation, because here we're just defining a function, but we apply it at nat. So these are sort of almost the same, but not quite, because in one case we don't know the value inside the body. And I guess I should also mention that there is another syntax for this, where you use have, and it looks, so the have has the same sort of format as the let, but have is actually equivalent to this kind of thing. It's just a lambda and then applying it, so you get the same behavior. Okay. Okay, so we can also, so this is the variable command. So if I wanted to have binders which I use in multiple functions, so here compose is going to want to be generic over alpha, beta, and gamma. Then I can put these variables up here and they will automatically get used in this function. Here, do twice only needs one of the variables, so but it knows that it's supposed to have type because it gets picked up because it's in this variable, and then variables live inside sections. Okay. One sort of word of caution here regarding a thing called auto-implicits. So, auto-implicits are a feature which, when enabled, will allow you to write something like this. So, alpha is currently not in scope anywhere. It's not been defined with a variable line, but I can write this anyway, and it will basically decide that alpha is a type in any universe, and so this gives you sort of more ML style typing, where you don't have to explicitly write the type binders. But this can be dangerous. So for instance here, maybe I wasn't paying too much attention and I thought that nat was spelled in lowercase, then I write this down, but this is not nat as in the natural numbers. This is just a type variable whose name is lowercase and nat. Now you can tell that this is happening in part because it's written, oh, that's extra fun. I'm trying to make a point here. Come back. So if I were to spell it correctly, then the variables will show up in white, and if I spell it incorrectly, then it shows up in red. Thank you very much. So this is how you can tell that you've made this mistake, but you can also just turn off auto-implicits, and that's what I've done for this project. So then it will just say, I don't know what this is. And so some people prefer this style, and I think that it's probably good for teaching purposes to keep auto-implicits off. But if you like it, then it's available as a feature.
Is this scoped just within a section, this option, or?
Yeah, so I've used a section here to scope this set option. So auto implicits in this project, and in this particular project, auto implicits are disabled by default, but inside the section, I've enabled it. So that's why when I exit the section, so this end corresponds to the beginning of the section, and when I exit the section, auto implicits are back to being false, but I should warn you that like in the default lean project, if you just create, lake new, create a new project, auto implicits will be enabled by default. So, thing to be aware. All right. So sections. This is a section. You can also name your sections. Naming doesn't mean anything. It can just be whatever you want. But it does have to match at the end. So that way you can at least tell where your sections begin and end. And sections will scope anything like variable, set option. There's also a bunch of other local instances. There's a bunch of stuff that's section local. Definitions are not section local though. They live, they live forever. Basically. You can also have namespaces. Namespaces are sort of like sections, but they change the name of the functions that are defined inside them. So I wrote def a, but I'm inside namespace foo, so I actually get something called foo.a. And when you're inside the namespace, you can refer to them without the namespace. So you write check a, and then it refers to this a here. Same thing for all of these. You can refer to them fully qualified like this, foo.a. And you can also, let me just mention this one here. So you can also do something like this. So you can say, if this is at all ambiguous, and you can be like, no. The one whose full qualified name is foo.fa, and that works. Outside of the section, you won't be able to refer to you won't be able to refer to A and F anymore because I'm outside of foo, but I can refer to them qualified with this foo dot prefix. And then also, if I open foo, then I can refer to them with the namespace removed, just like as if I was inside the namespace.
In the section you didn't indent, but if namespace you indent the code.
Okay, so the usual convention is actually to not indent sections or namespaces, but just to make it clear where they begin and end here, maybe I'll keep them indented. Okay. All right. So let me talk a little bit about
I have
dependent
a
types.
question about the namespaces. Would you use root to if you have the same name for like something in the namespace and outside, you would use root dot the name.
Yeah, exactly. So if I had, good idea. So let me. So if I check A here, that will not be an error anymore. But if I wanted, if I had A and then so now here, we actually have an ambiguity between the foo.a and the A which is available because it is right here. So if I wanted to say, no, not foo.a, I want root.a, then this is how I can disambiguate. Okay. Sure. So list.pawns is a function which takes it's prepending to a list, right? So it takes a head, then the tail, and then it produces a list. But it works on any type. So it also takes alpha, which is the type. So if we look at the full type, we'll notice that it starts with this thing where we have an arrow, but we also have a binder here, and this is called a dependent function. So Lean has dependent function types, and regular function types are actually just the special case of this, where it doesn't refer to the binder name. So all of these are actually dependent functions, where the first argument is this alpha. And here's another example of it. I mean, we've seen several examples of this already, where we're going to take in this is actually producing an element of a dependent sigma type. We're going to take in two type arguments. We're going to take in something of type alpha and then something of type beta applied to A. So this is actually, the type of this depends on this first value here. You can construct an element of a dependent sigma by just using these angle brackets, that is written like this. So that's useful. And this is just these two versions of the function. These are just the same thing. This is also a way to write the dependent sigma type.
Can I ask? So, if you want to instantiate the alpha of the list cons by hand, how do you do this?
This is coming. Okay.
Okay.
This is how you apply this function f. So you've got to pass it alpha, you've got to pass it beta. So here, if we say alpha's type, we want the first argument to be a type, the second argument to be an element of the same value of this first thing. Then I pass it a nat, I pass it the type nat, and then for the second argument, I pass it an element of nat, and then get the second. This is the second component of the dependent parent, and this gives us a nat. So this is just a way of combining all of those pieces together. And it works just like any other kind of function. But okay, so when you have dependent types, it often becomes the case that you can figure out values of types from other values that you pass in. So here's an example of list where I use just these regular binaries. So I say list takes a type, return it to type. Do the same thing for cons and nil. Now if I were to do that, then in order to call it, I would have to pass it nat, and then, so here I want to construct a list of one element, which is a 0. So first I have to pass the type, which is nat, then I pass it 0, and then nil, which also is waiting for the type, so I have to pass it in the nat. But Lean can actually figure out that this has to be a nat, because the second argument here, 0, is of type nat. So because of that, it knows that this can't be anything else. So it figures out that this hole is actually filled with the value nat. So to make this easier, especially in specific places, like in this case, where we have alpha is a type, then we can insert braces to say, I always want to do this sort of underscore thing. And so then it's going to not require it. So now this version of the function is automatically inserting the nat, but it's hiding. And then if we want to do the opposite, so if we wanted to pass in the value to a function like this cons prime, which takes its arguments using the braces, so implicitly, then we can put an @ sign before the thing. And now we pass it in, well, we don't pass it in, or we can pass it in the nat. And this is an alternative syntax here, where instead of using an @ sign, you can just say, I want the parameter here, which is called alpha, to be nat. So that's also a way of doing it. Okay, and this is the point where I realized that I went way too fast, because this is all of the material that I prepared for today's questions.
Yeah, but based on this, I hear the universe parameters are treated like differently.
Yes, yeah. So universe parameters are a separate kind of thing. So if you're familiar with Agda, then you know that universe parameters are an element of a type called level. Here they're not. Instead, they're in this special slot of universe parametric definitions, and you can't use them in other positions. So only at the top level of a declaration can you declare these universe variables. And you can actually declare, there's an equivalent of variable for universes, which is just called universe. So I could say universe u, and now it's available. And actually, I think I already did that earlier, so that's why it's complaining. Here I wrote universe uv so that I can write type u. If I don't do that, I think it won't let me. Yeah. So this is how you declare universes, and then you use them, and indeed, universe parametricity is different from just regular typing. And this has to do with the theory strength and how to make it not be too deep, not be inconsistent, basically. Okay, any other questions?
Is this like a variable declaration, this universe, but on this special kind of variables which are...
Yeah.
So they would also be abstracted if you were in a section or something.
Indeed, yeah. So the universe is also section local. Say yes and yeah. So it doesn't take effect outside of the section.
And other implicits also work on universes.
So universe variables are basically always implicit. Like they have this syntax that I showed where you can pass, you do this name dot and then you pass in the universe arguments here. But if you don't do that, then they're just implicit and inferred.
But if you were in like other implicit context and then in the declaration you type U, where U is not declared before, universe parameter.
Sorry, say that again?
Like if you enabled auto implicits and didn't have the universe UV line, would you have like errors for that you
Have universe. Wait, you're saying with auto implicit?
Mhm.
Ah, I see. So if I have auto implicits, then I think I can skip the others. Yeah, see, it's okay with this. Yeah.
How do I get this? Like after eval, you have the blue result. How do I turn this on?
This is the error lens extension. So if you just go to extensions, type in error lens, then install this extension, then it will do this thing where it puts your errors over here, and I like it. A lot of people like it. It's not a lean specific thing.
Yeah, could you quickly go over the at notation again? I was a bit confused by that.
So let's say that I have a function foo, and it takes a nat, and then it takes proof that the nat is equal to 1, and then it returns a unit. Very boring function. So if I want to, if I pass it a 1 and then a ruffle, then that gives me an element of unit. But it can actually figure out from the ruffle that the 1 was 1, right? So if I pass in nothing, it still says foo of 1 because that's the only value that would make sense there. If I know in a particular context that the argument can always be inferred, and that's usually going to be the case in functions like this where you have a dependency between the arguments. Like, given this one, I can always figure out x, because in order to pass this, it would have to be telling me what x is. So in this context, I would use braces in order to say, I want that to be inferred. When it is inferred, then I leave up the underscore. And so now I'm just passing away that. But maybe I want to pass that anyway. So I put the at sign, and now it's back to acting as though I had just the regular parentheses, right? And so now I can pass in, for instance, 0 plus 1, which is also correct, but is a slightly different input. If for whatever reason I wanted the version of foo where I passed in 0 plus 1 instead of 1. And the other thing that you can do in order to pass arguments is that you can specify them by their name. So this is nice when you have a function that has 17 arguments and you don't want to use an at sign and get like, half of them underscore underscore is very unmaintainable. So this is a better way to supply those arguments. Okay. So maybe maybe what we should do is just have you boot up Lean and make sure that you can do all the these things. Otherwise, I don't think that there's much more to say.
You could announce the next lecture. The next lecture will be on Thursday.
Yeah. Yeah.
Then
So,
not-
oh yes. Okay. So this Thursday we're going to be having another lecture, and then on next Tuesday we're actually going to be taking time off because we have some kind of FM retreat thing, and so I won't be here. So we will have next Thursday and then the Thursday after that. But otherwise, I think that's the end.
So, you meant next Thursday or this Thursday?
This Thursday will be we will be
At the same time?
yeah. Next Tuesday is the one that we're on.
So suppose you were to write that REFL is of type m plus 1 equals 1 plus n. Would that be acceptable or not?
Excellent question.
Okay, what is n there? Is that,
Actually, that's a good question.
I want to say for all n, of course.
Yeah, well,
Yeah.
it's the lecture.
Let's do this. There you go. So no, it does not type check. So n plus 1 and 1 plus n. There is a proof of this, but the proof is not REFL because one of those reduces to the successor of n, and the other one gets stuck because it's trying to do recursion on n.
Okay.
So if I do this with concrete n, then this works, but for the general n, it doesn't work.
I see.
Any other questions?
Kind of off topic, but what VS Code theme are you using? Because none of the default themes have the same highlighting as you.
That is a fair question. One Dark Pro.